the nice introduction. And so, first of all, hi everybody. So nice to be here, and thank you for the organizing committee for inviting me here. And I'm totally honored. And I promise in the next, hopefully 30 minutes, I will not send you to sleep. So make sure that you guys gonna awake all the time. So this one gonna be quite different from maybe in the same of the green chemistry, but could be different aspects that I'm going to be talking about. And so the title of my talk today is going to be Photocatalysis in Renewable Energy Production. And with a little bit of introduction, which is already begun. And so this is my research group, and we are focusing on photocatalysis at the moment, and the polymer from the carbon dioxide, and of course the biomass conversion from different catalysts. And I'm from Thailand, Chulalongkorn University, and the university is right in the middle of Bangkok, and with a lot of shopping malls surrounded. And if you cannot find your friends or your students, they might be getting lost around the colleges. And so our department is actually quite big, with 70 staff member and about over 400 to 500 students. And the university is about the same size as the universities like Indonesia, about 40,000 students. And of course, in our department, we have a whole range of the research, and we do catalysis and sensors, natural products. And at the moment, so the theme of the research in Thailand is also shifted towards more green chemistry. And so we also have the study program with the green chemistry and sustainability in our department at Chulalongkorn University as well. So in the past decades, with human activity, with transportation, we have all equally produced carbon dioxide. And carbon dioxide is the main greenhouse gas. And of course, 66% of the climate change has been actually attributed by this carbon dioxide, which we all over the world going to agree to reduce that carbon dioxide emission by 2030s, and hopefully, and it's really challenging to get it to zero emission in 2050. And so this is our world, and I cannot actually see Thailand, and I cannot find Indonesia either, so I'm not sure where we are in this world. And so anyway, so before, right, we used oil and petroleum energy sources, and by burning that or using that, we creating this carbon dioxide emission. But if we look at this diagram right here, we can find renewable energy alternatives. And you can see that we have hydro, we have wind, we have solar, and we have biomasses. And of course, as the topic already suggested you guys, the first thing I'm going to talk about is the solar energy, which is about 24% of this renewable energy, alternatives. And so by using the solar energy, the first example that everybody knows is the plant. So the plant used solar energy from the sunlight, which is really hot here and also in Thailand, to convert carbon dioxide into glucose. And also, people just always encourage you to actually, plant something near your house so it can, take away carbon dioxide and produce some oxygen. And of course, in the plant, there's a green stuff called chlorophyll. And this chlorophyll right here is the source for photosynthesis or even photocatalysis to happen. And so, sorry, where my pointer is it this one right here for the pointer? As in oops, sorry. All right, let me try something. Probably this one.
Mungkin operator bisa membantu untuk di next slide. You can say next, and the
okay.
operator will help you.
I'm trying to find the light on the pointer, but it's okay.
Oh, okay.
This one still works, but I cannot find the button. I have this one. Oh, sorry. Never mind. So in chlorophyll, right, you have two reactions that happening. It's all redox processes, which mean that there's a transfer of electrons in these cycles. If you look at the left-hand side on the screen right now, there's a water splitting. And if you heard of water splitting this day, it's a reaction to make hydrogen gas, which everybody think that hydrogen could be a new fuel for like transportation or whatever. And of course, in plant, you have light activated reaction. And in that, the plant converted water into oxygen by oxidation. And of course, the electrons that left in the process going to go down to this like electron transfer chain and producing this ATP. If we remember in our high school, that's what I only remember from biology, which is like the ATP, which is the energy carrier molecules. And that will help the next cycle, which is the dark reaction. So in the dark reaction or the Calvin cycles, plant gonna trap the carbon dioxide, and this carbon dioxide gonna undergo reduction and producing glucose and store in the plant. And that is the reduction process. So when you see this already, you know that plant is a good example of the natural photocatalyst. And so what humans are doing this day is to use this replenishable solar energy and trying to convert this energy into chemical energy. And so if you look at the diagram on the left-hand side, we have abundant, resources of water, carbon dioxide, nitrogen. And people actually start using something called solar fuels. And these solar fuels could come in form of heat, could come in form of photocatalysis, or could come in form of electricity from solar panel. And that all energy could convert all these elements on the left of the cycles into hydrogen gas, which is like the new alternative for energy, could go for the hydrocarbon, which in the technology right now, they focuses on C1, but people start publishing the work on C2 carbons or C3 carbons, which is going to be more and more useful and competitive. And the last one is, of course, they changed the nitrogen to ammonia, just similar to the nitrogen fixation cycle. And normally, when you heard of the ammonia, you know that people used to have this like Fischer-Tropsch process, and that used a lot of high energy and the catalyst, heterogeneous catalyst in a big reactor vessel. But this ammonia, they start publishing the work on ammonia on photocatalysis already. And of course, that energy, when you use it, it's going to turn into the electricity, something useful in chemical energy, and go back into elements in Earth and go around in the cycle again. And of course, this is almost like a dream, but it becomes almost real. So on the right-hand side of the diagram over here that you can see, it says 12. 12 is the name of the company along the West Coast in the US. Is where the Berkeley is. And this company is kind of like they work on sustainability and carbon dioxide capture. And that company has made SAF. So if you come across this word like SAF, it's sustainable aviation fuels. And normally, like traditionally, you would probably dig some, petrol, and then you kind of like, put through this oil refinery, and then you get some kerosene, and that kerosene would actually go for the fuel of the, for the plane, right? But this day, this company claimed that they trap the carbon dioxide with their technology from air, even passing the air through, get the carbon dioxide out of the air, and turn that carbon dioxide into the jet fuels. So the jet fuel is normally contain carbon of like C8 and above. So they use this like jet fuel in place of the kerosene. Before this sort of technology, rather than use the direct carbon dioxide, if in around our country or in Asia, we love to use the biomasses and change the biomasses into SAF and use SAF for the real aviation industry. So that's what they do. And the hurdle that you would actually have in terms of businesses, they actually claim that making it green is actually sometimes it comes with cost, and everybody know that. And so the world probably need our science to drive the cost competition and the new technology on this one. And so, making all that, you need something called catalyst, of course. And you probably know that with the catalyst, it's something that you put in your pot of reaction and you wish for something to happen fast. Fast is what you detect. But in the reality, that catalyst would actually lower the activation energy, providing alternative pathway for the reaction to take place. And hopefully that alternative pathway with the activation energy is much lower than the traditional process. And so you get this efficient catalysis, and you would wish that your catalyst is not going to be dead over the course of the reaction, because otherwise nothing would happen. And so what you wish for your catalyst, normally in any catalysis that you may do, you only wish, well, traditionally or the primarily, you wish for three things. First is selectivity. So if your catalyst were to produce so many products, you would wish that you have either one of those in really high amounts, so that you don't really have to separate them, or you don't really have to, purify them further. And secondly, when you compare the catalyst with some other people catalyst, what you actually say is the turnover number and turnover frequency. So the turnover number is the products that could be produced per one single site of the catalyst in specific amount of time. So if you can do it pretty long without the catalyst being dying, that means your catalyst is robust enough. And turnover frequency is meant to be the turnover number divided by hours. So you can see like how fast your catalyst is making the products. And normally in catalysis field, you are competing on three of these primarily things. But of course, in green catalysis, you will need more. And so everybody know that we have homogeneous catalyst and heterogeneous catalyst, and that is divided by how the phase of your catalyst compared to the media of the reactions. And of course, the list that we have here is the pro and cons for each catalyst. And this also applies to the photocatalyst as well, because in the photocatalysis, you still have it heterogeneous or even homogeneous catalyst. And so, sorry. I try to go back. Sorry, guys. So the common catalyst that you have in the photocatalyst, I found that in Indonesia, people do a lot of solid state chemistry with the oxide, with the sulfide, and those could be your photocatalyst as well. And of course, something look like graphene or even graphitic carbon nitride with the carbon and nitrogen, or even like, you probably know the framework materials, the MOF and the COF, and that is the framework materials. I skip the middle one for a second. And some other thing, which is like semiconductor and quantum dots. So the five names that I mentioned, apart from the transition metal complex, which I'm going to talk about it later. So the five names that I mentioned, the reason that they can behave as a photocatalyst is because they have this semiconducting properties, which like they have the two bands, valence band and conducting band, which I'm going to talk about in the next slide. And the transition metal complexes, you can use them in photocatalysts as well. So for example, if we go back to this chlorophyll, the chlorophyll in plant has a magnesium sitting in the ring of the chlorine ring, which means that is the transition metal complexes as well. And so how it works, it's to do with the change or the binding onto the metal center and the change in oxidation states and the coordination that go along with that. Okay, and that could be the light absorbing molecules as well. So these are the 6 types of the common photocatalysts that you probably encounter in your study or in any paper. And so how does this work? So today I'm going to focus mainly on semiconducting materials. And of course, with the semiconducting materials, you have been using it for like photocatalyst, of course, electronic, because it's you can conduct electrons and things like that, photovoltaic materials, and those sort of things that involving with electron transfer. And of course, in this case, let's see what happened. This is my student make the slide for me. So you can see the electron hopping in a second. And so with your semiconducting materials, one thing that you have, this material normally have a band gap energy. So the band gap energy is the gap between the energy gap between conduction band and with the valence band. And that conduction band, the light that hit the material need to have the energy that is higher than the energy of the conduction band. This is because when the light hit the material absorbs the light. The electrons will be activated, going from valence electron up, and up, going to the conduction band. And once you generated photoelectrons on the top in the conduction band, the bottom, you have something called a hole. And that hole, people understand that is a positive hole. Normally people call it like positive holes on the valence band. And when you want it to work, so for example, in the presence of oxygen, that electron could pass to the oxygen, or energy from that material could pass to the oxygen, producing that ROS, which is like reactive oxygen species on the top band. And of course, that oxygen species that receive the electron produce the superoxide radical species that could oxidize organic materials. You will see more pictures of that later on. And of course, now electron has gone to some other substance. So you're left with the hole. If you don't do anything with the hole, there will be electron jumping down to combine with the hole, and no reaction will happen, which means that it's equal to you not activated with light. So once you activate it, you want that electron to be useful, and you want the hole to be useful, and you have to fill the electron to the hole quickly, which means that at the bottom you can have oxidized products. And what I meant is, for example, you can oxidize benzyl alcohol on the bottom, on the valence band, to fill electron into the holes. And that benzyl alcohol would be oxidized into benzaldehyde, for example. And if you come across the concept, you probably come across something called sacrificial electron donor, which means that you need something to fill that holes so that your excited electron doesn't come down that fast. And you can use both of the electrons and the holes later on. And of course, the same thing happens if you actually have the the proton could be proton from water. That's how you generate the gas. So the proton in the water accepted the photo-induced electrons from the valence band, producing the hydrogen gas, which is green hydrogen, as you may know the term. And so if not hydrogen, that could be your carbon dioxide as well. So if the carbon dioxide received electron, it undergo reduction together with the protons. Sometimes you get some other gases. For example, is the carbon monoxide or methane that is more value added than the exhausted gas of the carbon dioxide. And of course, the whole, you need to deal with it. Either just put something in for it to oxidize. And if you put something more useful, it will result in something more useful as well. For example, you can instantaneously change the benzyl alcohol into benzaldehyde or into something called hydrobenzoin, which is the coupling reaction. So you can decide whatever, but life sometimes is not as easy as I talk about. And so this is how it works for the photocatalyst in terms of semiconductors. And so we look at these globes pictures again. The next thing that I would love to talk about is the biomasses. And everybody know that in Asia, the biomasses is what we actually have as a resources, because we do a lot of agricultural. And these biomasses can actually be used for something really important as well. And the market of this agricultural biomasses in Asia is probably one of the top tier in the world because we have so many. We in the lucky location when we have sunlight, we have water, and we grow a lot of plants. And so, for example, if you have the whole biomasses and you have, for example, one tree, you can have cellulose, hemicellulose, and lignocellulose or lignin. For the cellulose, that is the sugar, for example, and if you actually cut it down to the complete smallest unit, you get the glucose. And that glucose could go for like starting materials for some other, industrial or chemicals. And if you have hemicellulose, that's going to give you some other products that called FF, fulferol. And that fulferol or, hydroxy methylfulferol, HMF. I think a lot of Indonesian scientists are actually working on this fulferol and HMF as well to turn it into some other useful product by oxidation or even reduction to get some smaller molecules or bigger molecules for, polymers. And of course, the one that I can not ignore is the one that I'm using at the moment is the lignin. The specialty about the lignin is people don't normally eat lignin. People sometimes cellulose and hemicellulose is quite, in some plant is edible, but with the lignin side, it's not. Normally, you make clothes from that. And so what you do with the lignin is to chop it down into smallest part, and it gives you this aromatic ring on the left-hand side. And that ring is the bio-derived material on this phenol or maybe like benzyl alcohol that I talk about time to time. So with the biomasses, if you happen to be able to oxidize it, what's going to happen? HMF from the cellulose, if you're able to oxidize it, that is the furan dicarboxylic acid. Only one person actually successfully oxidized it using this photocatalyst. The good thing about furan dicarboxylic acid, if you remember the structure, it's the same structure as the PET. So there is a company in Netherlands that working a lot on this furan dicarboxylic acid, trying to make the Coke bottles that instead of using PET, they use the furan. And so if they successfully use the furans, then your Coke bottles can be thrown away and degraded because it's biodegradable and bioderived. And if you were able to oxidize this fulferol alcohol into fulferol, that is your pharmaceutical starting materials. And if you oxidize it into hydrofuran, that is the C8 to C10 for your jet fuels. And that is the area that people concentrated on as well, trying to oxidize this fulferol alcohol into hydrofuran. Or later on, they just hydrogenated it and making it into the SAF. And the last one that we are working on in the lab is to oxidize the benzyl alcohol into this benzaldehyde and hydrobenzoin, and that is the starting material for pharmaceutical and cosmetic industry. Okay, and after you guys have been listening to how it works in general for photocatalysis, I'm actually raising the example of what we do in chemistry in our lab at Chulalongkorn University. So we work on something like quantum dots. So basically, quantum dot, normally the one that you go to make the quantum dot normally could be the semiconducting material as well. And you make it into something smaller than the nanoparticle range. And when you have the particle range, nanoparticles, it's the nanometer sizes that could be up to 100 nanometers. But with the quantum dot, with semiconductor, you actually have it much, much smaller, less than actually 10 nanometers. And what you have the quantum confinement effect. You have the tunable band gap. by changing the composition, by changing the sizes, or by changing the capping agent. Why is that important? Because when you make the quantum dots and you're able to change all this, which means that you're going to tune it to the best condition of your photocatalysis that is possible. And of course, with something small in science, when something small, you know that it has like quite a big surfaces compared to the volume, which means that you can incorporating your quantum dots as a scaffold for something to hang on to that. And of course, I know that today is a bit green, right? But the materials that I'm gonna bring it up is the cadmium sulfide quantum dots. When people heard about cadmium, people just like, oh, so deadly. Every student and myself is still fine. Yep, it doesn't seem so green. But what I'm trying to tell you is sometimes life doesn't come as a package. So you want 12 principles, but I cannot give you 12 principles because sometimes you have to work on something that you know it lead you into that direction, but you have to equip it more with something else so that it can work better and become more greener. So in the end of the day, I think we will try to, divert it away from the cadmium sulfide to get it less toxic. But in the early pieces of work in the group, we try to make it more greener and more useful. I will tell you how in a second. Sorry, the slide keep changing. So, sorry, 1 second. So once I'm working with the toxic materials, what I try to do, I try to make it kind of like more selective, faster, easier to deal with, working in mild reaction, possible to scale up, and well controlled. And what I'm gonna tell you like in a few minutes, normally these sort of materials, when you say something photocatalyst, but that thing become, photocorroded, which means that if you keep shining the light onto some photocatalytic materials, sometimes they get degraded so easily. Well, you don't want toxic material, and you don't want the toxic material to get degraded easily. When it degraded easily, it will be no use. So what we did in the group was to stabilize it with some sort of polymers. So that polymer, I can tell you from now, is actually BES polymer or ionic liquid polymer to give it a bit more green and to give it a bit more, stabilized, and electron transfer would work better. So on the design, we actually working on this cadmium sulfide, but we bound it with the polymers that carrying the co-catalyst. Sometimes you need co-catalyst in these photocatalytic materials for electron to be transferred to the next active site. And so when the electron transfer to the next active site, the electron recombination with holes would be a lot less, which means that you preserved your catalytic activity towards the end. And so I might have to skip some of the slides because I'm running out of time. And what I'm going to tell you is we got this set up in our lab in Chulalongkorn University. That reactor is about 100 milliliter, which is quite big compared to other publications. And so we fill in with our catalyst, our polymers, and we use whatever that we want to bubble in and shine the light onto that. And so what we have, we already published the work on carbon dioxide, reduction. And so what I'm going to tell you is that strategy turned out to be working, which was lucky. So we get this cadmium sulfide to bound with the polymer and the co-catalyst, and we can boost up the reactivity up to 55%. And not 55%, 55 times. When you compare to cadmium sulfide alone. And of course, the other thing that we are doing at the moment and we can do in the lab is to produce green hydrogen at the same time as to oxidize this benzyl alcohol into hydrobenzoin. So which means in one go, we can produce two useful products. And that is on all photocatalysis. And of course, towards the end, we found that This is the cadmium sulfide. When it gets corroded, they become this black particle, just the cadmium zero itself. And so when we stabilize it, with the polymer itself, it becomes stable. Okay, you can see that. Whoopsie, sorry. Can we go to that slide almost to the end? Or maybe the conclusion page is okay. It suddenly switched it off. Okay, so the conclusion from now, we work with, unpleasant material that is not so green, but we try to find it from, chemistry aspects to put together everything and make it more kind of like greener by actually boosting the catalytic activities. And also what we try to do is to be able to recover that catalyst. Even it not going to be, reused many times, but when we actually put that polymer in, we actually kind of like separate it easier as well towards the end, so that we can separate out the toxic material from the reactors in the end. Can I have the last one slide, please? Could you move a little bit? Yes. So basically, that's summarizing all the work that we have done. We have done this cadmium sulfide. We find with all these activities, and if you are interested, we published in ACS Catalysis last year, and that is the first piece of work on this theme, CO2 reduction, and we will follow with another paper this year, which you already see our results. And thank you so much for the chance to deliver this lecture. Thank you.
Thank you, Madam. Please give big applause to Madam Junjuda. Please have seat next to me. Ya, ini mudah-mudahan saya bisa merangkum sesuai dengan apa yang beliau sampaikan ya. Agak deg-degan loh ini saya merangkum ya. Jadi pada intinya rekan-rekan dalam proses penggunaan atau produksi renewable energy. Jadi memang kalau kita runut ya, problems dari adanya climate change ini adalah CO2 ya. Nah, dan salah satunya untuk mengurangi CO2 itu adalah dengan menggunakan renewable energy. Tetapi pada akhirnya kita harus berpikir lagi untuk mengurangi CO2 ini tuh apakah ada alternatif lain. Nah, dan dalam hal ini penggunaan solar energy, biomass dan lain sebagainya itu bisa kita manfaatkan gitu ya. Kalau saya tidak salah menyimak tadi memang belajar dari sistem fotosintesis yang pada akhirnya sebenarnya CO2 itu bisa diserap kembali untuk bisa dimanfaatkan kembali gitu ya. Dan dalam konteks reaksi kimia ini adalah cara kerja dari electrochemistry. Nah, penggunaan green catalyst itu sangat disarankan dan diukur melalui 3 hal, yakni selectivity, turnover number, dan juga turnover frequency. Dalam proses photocatalysis reaction itu tadi dibagi menjadi 2, yakni aerobic photocatalysis oxidation dan juga anaerobic. Nah, dalam hal ini photocatalysis itu juga bisa digunakan untuk biomasa dan memang pada akhirnya produk-produknya itu bisa menghasilkan produk akhir seperti polimer, plastik, kemudian produk-produk farmasi dan juga kosmetik, jet fuel, serta sintesis kimia. Nah, dan dalam hal ini tadi juga disebutkan oleh Dr. Junjuda bahwa kebutuhan polimer itu dapat membantu proses dari reaksi kimia tersebut. Ya, mudah-mudahan saya tidak salah merangkum ya, rekan-rekan. Nanti kalau misalnya ada hal yang keliru gitu, tolong disampaikan ke saya agar tidak ada salah pengertian. Jadi setelah dari sesi ini berakhir, jadi rekan-rekan tercerahkan, bukan malah tersesat gara-gara saya ya. Baik, seperti biasa saya akan membuka 2 sesi pertanyaan dan sesi tanya jawab ya. Apakah ada 2 orang penanya? I will give the chance to 2 people who would like to ask about the catalyze. Yeah, 1. Okay. Yeah. Please mention your name. And yes.
Okay, thank you. My name is Liga from Ministry of Industry. Very interesting of your topic of photocatalytic. But my question will be really specific on the green ammonia production, because one of a new invention in green ammonia production is photocatalytic. In your opinion, which one better? You choose to produce green ammonia from electrocatalytic, water electrocatalytic, or photocatalytic, and how much the scale or like the small scale to produce the green ammonia from photocatalytic. Thank you.
Yeah, you can
Thank you.
directly answer that.
Yeah. So thanks for the question. So basically, in general, when you do electrocatalyst and photocatalyst, normally electrocatalyst is much faster and give you like bigger scale of the reaction, because what you do, you just like, housing your catalyst with electrons, and you can control what, how many electrons can go into the catalyst straight away. Normally you can do it in bigger scale in electrocatalysis, but in photocatalyst, normally you get it in milder reaction. So, for example, if you see from most of the work, people are trying to do photocatalyst in water, and normally it's to do with the light intensity, which is quite, one of the limiting agents. And of course, you cannot pulse electron all the way through, which means that photocatalysts normally give you less products. And normally, when you do this sort of electro or photocatalyst, you do in the lab is normally small scale. You do in 100 ml of water or 100 milliliter reactors. But in the actual fact, what you want to do, you don't want to do the flow reaction. So you keep flowing your substances in, and you shine the light or pulse it with electric cells, and that will work better than one batch reaction. And so normally when people reported something in this photocatalyst reaction, there are two things that you concern. Normally people would report it like, for example, millimole of ammonia produced per gram of catalyst per hour. But what people are trying to say, and in the end of the day, it turned into like apparent quantum yield, which means that how much light you put into that and how much electron from the light get used to produce the ammonia. And this is similar concept to when you have Faradaic efficiency. When you pulse how many electrons you can give from your electrical circuit, and how many has the catalyst been received and changed the starting material into the products. And that's how you determine which system is more efficient. Yeah, in each types. Yeah, that's the answer for me.
Ya, jadi tergantung kebutuhannya. So, are you meaning that if we would like to produce mass production for green ammonia, we need different types of product or catalyze, something like that?
You normally need different setup. Yeah. So because in the lab or in the publication, most people publish with the batch reactor, which means that they only do one single cell. But one single cell could give you little products. So what most people are trying to do right now, and it's challenging, is to use the flow cell, which means that you have the reactors, but your system is not totally closed for one system. You keep flowing the materials in, and you wish that the catalytic happen really fast. And when you flow in, you flow out, you get the product. That is the magic, right? So yeah, that's what you wish to do.
Ya, baik. Semoga terjawab, Ibu. Ya, oke. Next one. Ya,
Sorry, I keep asking.
no, it's okay.
So, yeah, I know that you are using cadmium, with some risk, and we know that cadmium is some toxic material. So, in the small scale, maybe you can still manage by using, some equipment, PPE, etc. But do you have any idea if this is implement for the larger scale? What will be the precaution to use that?
So that's a good question. So normally when people working in photocatalytic, they're still limited to small scale. So what I'm working with this cadmium sulfide is only like 25 ppm, which is really, really diluted. And when people want to scale this up, what they try to do, they just make the container bigger, the same light source, or they built the new light source to irradiate the whole thing. That would be quite difficult. What they try to do here, when I work with this is more colloidal or homogeneous. My colleague, the other one, he actually working in that by, have like coating the cadmium sulfide or even some other things onto the substrate, like glass substrate or any other solid substrate, so that once you actually working and finishing, you can take off the substrate, and that would be more controllable. But that would be, you have to weigh it out between when you work on heterogeneous, sometimes you can deal with the catalyst easier, but the production is not as fast. But if you do homogeneous, your production is much faster, but you will be bothered to separate out that cadmium sulfide before you dump into, some sink or whatever. Yeah.